Okay, Lab 3.1 due tomorrow. What do we got to do? Well, here is the Lab 3.1 analyzes video from your classwork. So if we go back over here, your classwork, you did this the other day. This was under your classwork. You're actually going to submit the lab under here, Lab 3.1 ball drop. So with the analysis that you saw from before, what you did before, uh, you have to, over here, pull up the video that you made. And then from the video you made, you came up with some data. So here was the YouTube I made for you. YouTube is right here. Let me jump up to where it matters. Hey, be quiet back there. So this is the key point. So we had an analysis, a displacement versus time graph. And then a little later in the video, we did an analysis with a velocity versus time graph. So the displacement versus time graph, let's look at that first. And let me break down how you're going to analyze this thing. Let's see. We are in YouTube right now. Just shrink this. Bring this over here. We should open it. Bring this over here. Let me just give you the breakdown on how you're going to analyze this business. So by the way, you are going to submit your actual video file. So attach your actual video file to the assignment. And I would, of course, have to open it with Vernier. I'm not going to be able to open it any other way. Don't give me a PDF or anything else. You got to download it. Find where you downloaded it, rename it with your name and Lab 3.1, and submit it to this assignment. Okay, so over here, the way you're going to analyze this is to recognize that that first graph at about 12 and a half minutes into the video, your axes are kind of like this. This is it says Y, but the Y actually means it's displacement, it's in meters, versus time in seconds. And your graph looks something like this. You should have this quadratic curve downward here. Now, in your graph, there was actually an A, a B, and a C. I'm going to make up numbers here. You have to do your actual numbers. A, let's say, is somewhere around -5. I'll keep it easy. The B was somewhere very small. I'll put 0.01. And the C also was very small. I'll put 0.00, Okay. So what are these things? Well, D versus T graph. Actually, what you're seeing here is displacement as a function of time has an equation. And the equation is, from your reference table, DIT plus 1/2 AC squared. Okay? Now, at first, you might say, all right, well, what does this have to do with our y equals ax squared plus bx plus c, these being our a, b, and c? And the answer is it's the same equation. It's actually the same equation. In this case, the y is, let's see, let's switch up colors. Here we go. The y is the displacement. The x is the time. And that's not surprising. The y-axis is displacement, and the x-axis is time. So if you start to recognize the parallels, then these A, B, and C actually take on meaning. And let's see what that is. Well, we need to rearrange our equation down here so that it looks like this one up here. Well, that's easy enough. Notice the x squared term is first. So let's move our x squared term first. So displacement equals 1/2 acceleration times squared. Then the x term is second. So let's move our x term second, plus VIT. And then we have this c term. And for hours, we don't have anything written there. But actually, you could put a term there. You could put, it's really your initial position. It's DI. And we don't have that in our course. That's kind of built into the displacement. However, this parallels this equation down here parallels this equation up here. These two are actually telling you the same thing. And once you recognize that, you now can make sense of A, B, and C. This is the coefficient, that means the number attached to t squared. This is actually what we call A in our quadratic. 1/2 acceleration is A. Let's switch colors. VI is attached to t to the first power, is the same thing as b attached to x. VI, initial velocity, is b. And then, finally, going orange. Finally, the initial displacement here is the c from this equation. And so from this, you actually can figure out a number of things. Realize that 1/2 acceleration is, in fact, A. Maybe you say, wait a minute, what are you talking about down here? Let's scroll down a little more. Let me get you a little bit of space down here, extend this page. Okay. If this is the same thing as the letter A, this is the same thing as the letter B, and this is the same thing as the letter C, well then it's not too much of a leap to make an equation to connect A, B, and C. And the connection is simply as follows. 1/2 acceleration equals A. Initial velocity equals B. Initial displacement equals C. Now, all you got to do is plug in your A, B, and C up here and figure out what is the actual acceleration, what is the initial velocity, and what is the initial displacement. Now, please be careful here. Don't confuse the letter A. We'll use a highlighter on this. Don't confuse the letter A with the acceleration. They are not the same thing. Just because they both have a minuscule a, it does not make them the same thing. In fact, the way to do this is pretty straightforward. Let's go back to red. Since the initial displacement equals c, you can then make the comment the initial displacement equals 0.002 meters. Fine. Since the initial velocity is b, you can then make the comment initial velocity is 0.001 meters per second. Since 1/2 of the acceleration is a, you can make the comment 1/2 of acceleration equals -5 meters per second squared. Fine. Of course, the first two are done. We know the initial displacement, we know the initial velocity. You must then solve for the acceleration. This is very easy to do. I'm not doing this division step for you or multiplication step. You must do it yourself. Very quick, very easy. So you're going to come up with the acceleration, the initial velocity, and the displacement. So I'm going to give you a Google form. What you're going to fill in are A, B, and C from this, from your quadratic, from the program. And what you're also going to fill in are your initial displacement, initial velocity, and acceleration. Good. Next, if you jump over to about 1620, 1630, you don't have to jump, just follow me. You have the linear, the velocity versus time. And so this one I'll draw a little more quickly because it's the same thing we just did. You have a velocity versus time graph, which was roughly like this. I know it was not perfectly straight, but your curve fit did come out straight. You did a linear fit. And in this case, they provided the equation y equals mx plus b, and they told you m, which was, depending on who you were, maybe it was around -9, and b was hopefully a small number, let's say 0.01. Fine. Same game. This is velocity, this is time, Do we have an equation for instantaneous velocity as a function of time? Yes, we do. It's Vf equals Vi plus acceleration times time. There it is. This actually is y equals mx plus b. It's the same equation. In fact, if we just do a slight rearrange, we get Vf equals acceleration times time plus initial velocity. And so, again, we're going to go much more quickly on this one because it's simpler and it's the same thing as we did on the previous page. The Vf is the y. This is the y-axis. The time, so Vf is the y. The time, V, is the x. That's all. And so if you recognize here, oh, this is actually pretty simple. Acceleration, therefore, must be m. M is the slope. Initial velocity must be the b, aka the y-intercept. So it's very easy now to come over here and say, well, the acceleration is m, and the initial velocity is b. And then based on these two, you can very easily come in here and say what they are with units. Meter per second squared, meter per second. Okay? And then I'm going to ask you a couple little questions on it. And that's it. That'll be the finalization of this part of this lab.